Well, I'm wondering if you own a toothbrush like this one, if you brush with a regular manual toothbrush or if you use an electric toothbrush. If you happen to use an electric toothbrush, I want you to do something right now. Go get it. I'll wait. Press pause if you need to. Go on, go grab your electric toothbrush. Okay, hit pause, go get it, and when you come back, resume the video. Okay, so you're back with your electric toothbrush. Now, let's take a close look at it. There's some cord that plugs into the base. And then look carefully. I think every point of contact between the toothbrush and the base is all made out of plastic. I don't think there's any exposed metal parts. So that's kind of curious. How in the world does the electricity from the base make it into the toothbrush when it's recharging? So let's take a look at this. Let's remove the base and the toothbrush for a moment and see how they fit together. So on the base, if yours is anything like mine, there's just a little tiny nub of plastic that sticks up, and then there's a cavity in the bottom of the base of the toothbrush. And so when you put this down onto the base, they fit together, but still it's plastic contacting plastic. That doesn't seem like it should conduct any electricity. So if you ever had a chance to take these apart, here's what you'd find. Inside of this base and up into that nub of plastic, there's probably some material that is steel or iron or something with a high relative permeability or susceptibility, and around that is wound a solenoid with several windings. And that's basically what goes off to the plug, probably with some other circuitry. Okay, and then inside the plastic of the actual toothbrush, there's probably another one of these iron or steel cores, and then there's some wire wound around that one. Maybe not quite as many windings, maybe something like that. And then those go off to the battery or whatever stores the electricity inside of the toothbrush. So somehow a signal travels from this coil of wire. We'll call that the primary because it's the one that directly receives electricity from the outlet. And the signal from that primary is able to send a current into, I guess we should call this then the secondary. In other words, the base and the toothbrush itself form a sort of transformer. And by the way, the outlet is providing 120 volts. And I don't think you want to directly power your toothbrush off 120 volts unless you've got really, really bad tartar buildup on your teeth and you need to chisel it off. But the point is, I think you've seen these travel versions of these toothbrushes, and on those, I don't know, maybe all it requires is something like 2 1.5 volt batteries. Maybe this thing only operates on 3 volts, maybe 6 volts at the most, but certainly not 120 volts. So not only is it a transformer, but we say it's a step-down transformer because it's reducing the 120 volts down to either 3 or 6 volts. So to get a better idea of how transformers work, I want you to draw a picture. And they work all based off of Faraday's law. So draw this. Just draw a box. Actually, instead of a box, make it look more like a frame. And then if you can, make it look three-dimensional. So something like that. Even make it look three-dimensional on the inside part of the frame. So maybe something like this. If you drew it neater than I did, then maybe you've got it like this. Let's add something to your drawing. If you have different colored pens, you can do the same as me, but otherwise you can just use pen or pencil. Let's imagine taking a piece of wire and wrapping it around the left side of this frame. So the wire is going to come around, and then it's going to tuck behind here, and then it disappears but reappears back over here, and then disappears and back and comes around. Okay, so you can wind this around, several times. I don't know exactly how many. Just make it look like it winds around over and over and over again, multiple times, till eventually the wire comes back here. And so if you've got a different colored pen, you can do the same thing on the other side, but over here on this side, make a smaller number of windings. So maybe you've got something ultimately like this on the right. So if you kept up, now you have an image that looks more like this one. So this is a schematic drawing of the basic components of a transformer. We have a secondary coil, as well as a primary coil. And we'll learn in a later unit that if the number of windings in the primary coil, maybe we'll call it N1, how about if we had to count them in this case, 1, 2, 3, 4, well, anyway, N1 is greater than N2. 1, 2, 3, yeah. N1 is greater than N2 in this case, and that's an example of a step-down transformer. If it were the other way around, if N1 was less, or if N2 was greater than N1, then we would have a step-up transformer. Okay, so how do these transformers work? Well, you send a current into the first coil. So if that was the case, if we just had current flowing in this direction, then use the right-hand rule, curl your fingers in the direction that current would flow in the primary coil, and see if you can figure out the resulting magnetic field. That primary coil would behave like an electromagnet. Oh, especially if this frame that it's wrapped around is made of iron or steel or anything else that has a high susceptibility. Yeah, right, so the magnetic field lines are going to point like this, aren't they? Upward through that primary coil. Then the primary coil is just like a solenoid wrapped on an iron core. It's an electromagnet. So there's our magnetic field lines, except I'm drawing them as if they would curve and stray, but because we're imagining the core is made out of iron, remember those bundles of atoms that group together and reinforce each other we call magnetic domains? The magnetic domains are going to align, and so these magnetic field lines actually look more like this. They travel through the iron and form closed loops on themselves without spreading out and diminishing all in space. They're all contained within the iron. So look at this. The magnetic field of the primary coil, well, those magnetic field lines are pushed, so to speak, through the secondary coil, which means the secondary coil now has some magnetic flux. It has a product of magnetic field, and for sure this secondary coil has a cross-sectional area to it. So when we have the product of magnetic field and area, we have flux. So if there was no current at all in the primary coil, then there'd be no magnetic field lines and there'd be no flux in the secondary coil. Now remember what flux does, right? Yeah, absolutely nothing. Flux doesn't do a thing. What we need is a rate of change of flux. So if there's a steady amount of current, then there's magnetic field lines, and if the core that they're wrapped around is made of iron, those magnetic field lines are pushed through the secondary coil, and because of that, the secondary coil has flux, but if that's a steady current, it's a steady flux, and so d phi dt would be 0, and there'd be no output voltage on the secondary coil. But that's not how transformers work. Transformers require AC, right? A steady current would be a source of DC, and DC is never used on a transformer. Transformers always use AC electricity. And the special feature of AC is for a moment the current flows this way, but then it reverses direction and flows back this way, and then it flows to the right, and then it flows to the left. So for a moment, the magnetic field lines inside of the primary point up this way. But then a moment later, the magnetic field lines point down in this direction. And those magnetic field lines cause the domains of the iron core to align, and the field lines form closed loops through the full iron frame. And so the magnetic field in the secondary coil initially points down, but then it points up, and it oscillates just as the current in the primary coil is oscillating. The magnetic field passing through the secondary coil is oscillating, which means not only do you have flux, but in particular, there's now a rate of change of flux in the secondary coil, which means there's an output voltage in the secondary coil. So an input voltage is associated with an input current, and as long as that input is AC, then there'll be some output voltage, and you could use the primary coil to send a signal to the secondary coil without any direct electrical contact. Notice there's no current that makes it directly from the primary coil to the secondary coil. It's not a current that's being conducted, it's a magnetic field that's being passed, and more particularly, it's a alternating magnetic field that's being passed through the secondary coil. And so in another future unit, we can explain how the output voltage compares to the input voltage if we know the exact ratio of the number of windings. Oh, another detail about these transformers. If you ever bother to take one apart, you'll notice that the iron core isn't solid iron. It's usually made of several iron plates that are fused together or stacked together. So if you look at it, you'll see several wafers of material that have high relative permeability, all sandwiched together so that it looks something like this. Now, why is that the case? Why are the transformers made with this sort of design? Well, as these magnetic field lines are carried through the iron core due to the alignment of the domains, iron itself is a conductor, so we could see, like, imagine this as a loop of iron. Well, as the magnetic field lines alternate in direction through any imagined loop of the iron itself, there's a change in flux, not just in the secondary coil, but there's a change in flux in the iron itself. And so that would produce those currents that we call eddy currents. And so you'd have this iron core with magnetic field lines that for a moment point this way, then come back this way, and we imagine the iron core as being several loops all stacked together. Then each one of these loops has current that's changing direction in it. So the current runs this way, and then it goes back the other way, and we call those eddy currents. Well, the eddy current would then be wasted as heat, right? Remember that power is current squared times resistance, and so there's a heat loss. And instead of your input energy in the form of electricity and current of the primary coil making it to the secondary, it's all wasted away as heat, as thermal energy that can't be used for anything good unless you make it in this wafer design. And then you can't have any large-scale eddy currents, and so there's very little heating. Although I'm sure you've seen these sort of plugs for all sorts of appliances in your house that are the big, large, boxy plugs that look something like this. Right, maybe they plug in. Very rarely do they have a ground wire on them because these are used for devices that would otherwise only be powered off of 3 volts or 6 volts or something. So then this goes off to maybe like, I think there's a pencil sharpener in your classroom probably that plugs into the wall outlet with a plug like this. So These are really heavy if you hold one of these in your hand. Now, why are they so heavy? Because they have some sort of an iron core. All transformers require a frame for which the primary coil and secondary coil are wound around so that you have something with a high relative permeability. Okay, and then what else do you feel when you hold these in your hand? Well, if they've been plugged in for a while, not only are they heavy, but they're also warm. So they're not hot like they would be if it was solid iron, but they're at least warm. You can't completely get rid of eddy currents, but you can minimize the eddy currents if you make it out of this sort of a wafer design. Okay, so there's your introduction to the transformer.